Yes, Pasha. So next week we'll be starting to go over some actual hand calculations we can do involving finite elements, and the midterm will be based on that. Yeah, we haven't gone to that point yet. So the early part of this class is really just focus on using the software effectively and learning all the concepts that go into that. The conceptual stuff comes in the second half of the class. All right, it's 3 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Great. Good. Sure, kind of reminds me of COVID, just kind of talking to a computer and everyone's on Zoom. Okay, so today we have a busy day today. So it's another ANSYS activity day. So we finished ANSYS activity 1 last Thursday. Or was it Wednesday? I think it was Thursday. And we're already doing ANSYS activity 2 today. So that'll be in the second half, just like we did last time. But before we get there, I do have a lecture on elements. And so up until this point, we've covered all of the essential basics of finite elements. You've been introduced to the ANSYS interface and how that works. And we've gone over all the basics of meshing, boundary conditions, and material properties. And so those are all the essential ingredients. Now we're kind of ready to start diving in a little bit deeper into some of those concepts, starting with the mesh. And so this week is going to be all about the mesh. So today we're going to go over 2D element types. We're going to talk a bit deeper in terms of how the shape of the element really affects the results. We'll talk a bit more about element order today and how that affects the results as well, just so that you have a stronger understanding. Because last week when we went over meshing basics, we had mentioned all these topics, but we didn't really talk about why these things matter the way that they do. And so we'll go into a bit of that today. Okay. All right, and so besides that, so activity 1 was due on Sunday, so I haven't gotten around to grading it yet. I've kind of been busy with other stuff. I do plan on grading that sometime tomorrow. Activity 2, just be aware it is a very quick turnaround because I don't want too many assignments overlapping. We are planning to do ANSYS activity 3 on Thursday, and so ANSYS activity 2 then is going to be due on Thursday night. And so you're only going to have a couple days to do it. It's not a very long activity. I mean, none of the activities are anything that long, and we do most of it in class together. But just be aware of that short deadline, just so that you don't get it in time. Okay. I am also working on the specifications for your midterm project. So midterm project, it's already coming up, so it's not due this Sunday, but the next Sunday. But I do plan on getting that out to you guys by tomorrow. Okay, so tomorrow we will talk about the midterm project in terms of what is expected, just so that you can get started on that as well. Okay, once we're done with ANSYS activity 2, technically, once we're done with ANSYS activity 3, that's kind of all of the basic ANSYS. But even after activity 2, you can already get started on the midterm project. So I think tomorrow is a good time for us to introduce that and talk about it. Okay. All right. Any questions I can answer about anything before we get started for today? Okay. All right. So let's go ahead and get started. Okay. So today is a bit more about mesh or in particular element types. Okay. All right. So today, the main topic is to go over the main 2D element types. So the rectangle, the triangle, linear, quadratic. But in order to kind of get there, I do want to talk a bit more about how finite elements actually find a solution to a differential equation. Okay? Okay. So let's start with finite element approximate solutions. Okay. We kind of need to talk about this first, before we start getting into the nitty-gritty of all the different element types. Okay. Okay. So first thing I'll say is something I've been repeating. Yeah, I think I've said it, 2 or 3 times every single day of the summer so far, is that finite elements at its core is really just a methodology or a technique for solving complicated differential equations. Okay. So last week we introduced this. We introduced the concept of a boundary value problem. We talked about the different types of governing equations that are out there. Again, mostly we're dealing with structures in this class, but you can also use FEA for heat transfer fluids, electromagnetism as well. Okay. Now, we didn't really talk much about how it occurred or how this happens, right? We just kind of, at this point, we've just kind of accepted the fact that FEA can solve these differential equations. So let's talk a bit about how that's actually done. Okay. So, maybe a way that we can qualify that previous statement is that, FEA doesn't solve for exact solutions to these differential equations. At its core, FEA is solving for approximate solutions. Okay. All right, and so that term there has quite a few meanings. And so on the one hand, we're not solving for an exact solution. Okay. There is going to be some expected error, right? And so it's the whatever you get for an approximate solution, it's never going to be as precise as the exact solutions. Okay. But that's a trade-off we're willing to make because, if you were to try to find an exact solution to the differential equations on such a complicated geometry, that's practically impossible, or just not really feasible for most problems. Okay. But that term approximate also means that we're going to change our approach. And so the way that FEA actually solves the differential equations is actually quite interesting. Okay. And it's actually, a very different approach, I think, to some of the problems that you've probably done in your previous classes. Okay. So in your previous classes, when you're presented with an equation, when you're presented with a problem, I always call those kind of a straight up solution, a straight up, approach. Okay. Or we can say that, we solve those equations directly. Okay. And so when you solve an equation directly, you don't really make any assumptions in terms of how the solution looks like. You just solve the problem. And then whatever the solution ends up looking like, that's just what it ends up looking like. Okay. So think back, last week we did that very brief example with the first order ordinary differential equations where we took that integral, right? When we solve that, and so, just to kind of refresh your memory, right? So this is the equation that we solve. And so when we solved this equation, we had no idea, we had no preconception in terms of what the solution would look like. We just integrated the equation and the solution just ended up what it was, right? So a direct approach is great when you have techniques to do so, right? And we have techniques to do so mostly for simple cases. So one-dimensional problems, simple geometries, right? And that usually nets us an exact solution, okay? But FEA doesn't actually work like that. FEA doesn't actually solve these equations directly. What it does instead is that it first assumes what's called a form of the solution. Okay? And so before we even start solving the problem, what FEA does is, all right, we're going to find the best linear function that solves this equation. We're going to find the best quadratic function that solves this equation. Okay. Right. And so before we even solve the problem, we make this assumption in terms of, what the solution actually looks like. Right. Oh, and then what it does from there is that once we have assumed the solution, we then solve what FE is going to do is going to solve for these unknown constants, A1, A0, A2, in order to best fit this, in order to best fit the governing equations. Okay. All right. And so by doing so, we get a solution, and it's through a way that is, much easier to do through a computer. We're not going to go through the exact details of this in this class. That's kind of more a topic for the graduate level. But just know that this process is a lot easier for computers to do than a straight up approach. When you're looking at the more complicated geometries and more complicated symbols. Okay. But this approach does have its weaknesses. It does have its limitations. Okay. And so when you assume a form of the solution, and so when you assume the form of the solution beforehand, you kind of lock yourself into what the solution is going to look like. And any type of solution behavior that occurs outside of your assumed form is really kind of impossible to account for. And so what that essentially means is that, if we were to solve our original equation here, right? So the d squared dx squared is equal to 3x squared, right? If we were to assume a quadratic solution to that, we're kind of locked into our solution looking like a quadratic function, right? And a quadratic function can only do so much, right? So it essentially just looks like a parabola, okay? But if our exact solution, our underlying exact solution had something other than a quadratic character or behavior, then there's no way we can really accurately account for that in our solution. Okay. And this is actually best illustrated by that example just there, right? And so if we take this differential equation here, so I'm not going to solve it completely like we did last time, but let me just kind of show you really quickly. Okay. Right, so let's say this is our governing equation right here. Okay. Right, so if you remember from last week, the way that we solved this was that we took the integral of this twice in order to solve for u. Let's just do that really quick. Right, so I'm using shorthand notation here. I'm integrating twice with respect to x. Normally you would do this kind of one step at a time, right? But what you obtain from this is u of x is equal to 1/4 x to the fourth plus c1x plus c2. Okay. Okay. Now, the term I want to draw your attention to is this one right here. Okay. The first term in our solution. So by the way, this equation here, this 1/4 x squared plus c1x plus c2, we obtained a solution by solving our equation directly, right? So this right here is what I would call our exact solution. Okay. So a 1D differential equation we can solve exactly just because it's simple enough, right? Most of the time, for most problems that we're going to solve with FEA, the exact solution is not available to us. If it was available, there's no point in running FEA because we can get the exact solution. Okay, I'm only using this just as an example to illustrate the shortcomings of an approximate solution that FEA is going to do. Okay. Okay. Anyway, back to this term here. Okay. Okay. So the exact solution is telling us that there's one component of our exact solution that depends on x to the fourth. Okay. Right. And so another way that we can describe this is that our solution has an x to the fourth character or behavior to it. Okay. Now, if we look at our assumed solution, right? And this would be if we were to solve this using finite elements, right? So this is the assumed FEA solution. Okay. So let's pretend that we're solving this equation from scratch using the finite element method. Okay. And so our assumed solution is A0 plus A1x plus A2x squared, right? So we're assuming a quadratic solution. So if you look at our assumed solution here, you'll see is that there are no terms here that have x to the fourth, right? So no matter what we obtain for the coefficients, so no matter what we solve for A0, A1, A2, it will always be impossible for this assumed solution to match the exact solution exactly, just because it doesn't have that x to the fourth term to it. Because x to the fourth is fundamentally a different type of function than x squared or x or a constant. Okay. Okay, so that's one thing to kind of keep in mind, as we're kind of discussing the different element types and the different shape functions and the different orders. Okay. And so kind of the upshot for all of this is that, generally speaking, the more terms that you have in your assumed solution, the more flexibility or the more accurate your approximate solution is going to become. So that right there is kind of the upshot of this entire first 20 minutes or so of the class. Okay. Because what we're going to do, today is we're going to look at all the different element types in 2D, the 2D quadrilateral, the 2D triangle. We'll look at their linear version, the quadratic version. And what you're going to see is that each of those elements have something called a shape function, where the shape function is essentially the form of the assumed solution, right? And so certain types of elements in certain orders are going to have more terms associated with them. And then that's going to lead to better or worse accuracy. Okay. But hopefully this kind of gives you a bit more context in terms of why certain elements are going to have better accuracy, just because certain elements are going to be able to model or be able to capture certain types of solution characteristics that other ones don't. Okay. And then by the end of this first half of class today, before we get into ANSYS activity 2, we'll talk about kind of one actual real life, consequence of this, which is a phenomenon known as shear load, which is something that you want to avoid when you're running structural type simulations. Okay. Okay. Any questions on this so far? Okay. Good. Okay, so with that, let's go ahead and get into the different element types. And I'm actually going to go a little bit reverse in terms of what I have in the actual notes. Okay, so let's talk about the simplest 2D element first, which is the linear triangle. Okay. All right, so up to this point in the class, we've only just really discussed one-dimensional problems, which are good just because 1D problems we can actually solve, but there's no point in using FEA for a 1D problem because we can solve it, right? So for the most part, when you're taking a class like this, a lot of times the discussion starts at 2D problems because those are the ones that end up just being more interesting for fun analysis. Okay. Okay, so let's look at the linear triangle. So the triangle, you can do this. Okay. So we have 3 nodes here. So 1, 2, 3. It doesn't really matter which ones you label 1, 2, and 3. We're just counting the nodes. Okay. Okay. And so, like I mentioned, every element type has something called a shape function, where the shape function essentially gives you the form of the assumed solution that it's going to take. So that's the definition we're going to go for. The shape function actually plays an even bigger role than kind of what we're going to talk about in this class. But again, that's kind of more of a graduate topic. Mathematically, the shape function kind of determines a lot of behavior of the elements, even in terms of how it determines the shape of the element itself. Hence the name shape function. But the way that we're going to use it, the way that we're going to interpret it is we're just looking at the functional form, okay, and what that means for our solution characteristics. Okay. So our shape function for this one, and so for the shape function, I'm going to use the symbol n. Okay. So for a linear triangle, our shape function is going to be a function of x and y, just because we're in 2 dimensions. Looks something like this. And so we have a0 plus a1x plus a2y. Okay. So this is the simplest shape function that we're going to get in 2 dimensions. Okay, let's break it down first. And so what you're going to see here, and what you're going to see this for every single shape function, we have what's called our constant term. So the constant term is a term in our shape function that doesn't depend on x or y or any of the spatial dimensions. It's just a constant. Okay. So the constant term has to be there. There's no negotiation. So I sometimes I get asked, can you make a shape function without the constant term? You can. It's just not going to work. It's going to give you a wrong solution. So every shape function, no matter how complex, even when we get to the 3-dimensional shape functions, the constant term has to be. Okay. Next one we have here is a1x. Okay. So this is our first linear term, and so from this we can see this term we say it's linear in X. Right? It's linear in the sense that X has an exponent of 1, and it's an X because it's X. Okay? Right, and then finally we have A2Y, which is the term which is obviously linear in Y. Okay. So it's a multivariable function just because we're in 2D, right? And so every 2D solution is going to depend on both X and Y, just because those are our spatial coordinates, right? And true to the name here, for a linear order triangular element, our shape function is also linear order, right? So we have no terms here that are greater than linear order, right? So everything has an exponent of at most 1. Okay, good. So when you solve for a finite element solution using the linear triangle, this is the shape function that you're going to plug in. Right? Now, another thing that you may have noticed is that overall we have 3 terms here, right? We have the constant term and we have the 2 linear terms, right? So 3 terms in total. That should match, or maybe you've noticed that matches with the number of nodes that we have in the element. So a linear triangle has 3 nodes, and so that means our shape function has 3 terms in it. Okay, and each term that we add, we're just adding kind of future complexity to that. Okay. So that's not a coincidence, and so in fact that's going to be a trend that's going to carry us up until tomorrow's lecture as well into 3D elements. And again, this is I'm going to say this a lot over the next couple of days, but it's we're not going to get into the details about kind of exactly why that is. Oops, spam follower. But it has to do with what's called solution continuity. Okay. So, I'll just mention this. This is not something that I'll write down and expect you guys to know. But, if you think about our activity 1, right? When we looked at our mesh was a collection of a lot of these different elements that were all kind of connected together, right? The expectation, and in fact, the FEA kind of relies on this fact, is that when you go from one element to the next, right? So let's say there's a neighboring element that's right next to it, like this. Okay? So when you go from one element to the next, the solutions should be continuous in the fact that there should not be any kind of weird jumps on the solution. Okay. And so part of the way that we enforce that, or part of the way that we make sure that happens, is by making sure that the solutions at all the nodes match from one node to the next. Okay. And so for every element, what we essentially do is we enforce matching solutions in between nodes, or excuse me, we enforce matching solutions at the nodes in between elements. So that way, when you go from one element to the next, you have a nice, smooth, continuous solution. Okay. And to do that, you need to have your shape function needs to have the same number of terms as the number of nodes in your element. Okay. Okay, but that's just kind of an aside. So, essentially, what all you guys have to know is that, the number of terms or the number of, or the complexity of your shape function really just depends on the number of nodes in your. Okay, any questions on this so far? Okay, good. Okay, so that's the linear triangle. So again, this is the simplest function that we can think of. We only have 3 terms in our shape function here. And so, like we kind of just discussed beforehand, that kind of really limits the types of solution behaviors that you can actually do. Okay? So let's step up. So let's look at the next triangular element. Let's look at the quadratic triangle. Actually, let's do this instead. Let's go to the quadrilateral just because I want to kind of illustrate something here. So let's do 2D element type. Okay. So we'll stick with the linear first, but this time we'll look at the linear quadrilateral. Okay. Okay, so our linear quadrilateral has four nodes, just because a quadrilateral has four sides, right? So we need four nodes to comprise the shape. Okay. And so the fact that we have four nodes here means that our shape function can have one additional term in its expression. All right, so if we look at the shape function for the linear quadrilateral, it looks like the following. Just like we started with the linear triangle, we have to start with the constant terms. We'll start with A0. Next, we have the two linear terms, and so we have both A1x plus A2y. Okay. Makes sense because we have a linear, our shape, our element here is still linear order. And so we should have those linear expressions in our shape function. Okay. But we can add one more term, right? Just because we have one additional node here in our element. But, we're kind of limited in the fact that we're not exactly limited, but, if we're going to go based on the naming of this element type here, we're limited to just linear terms, right? Linear meaning that, the exponent of our spatial coordinate should not exceed 1, okay? But we've already kind of run out, right? So we've already used A1x and A2y. So there doesn't seem like there's any kind of linear terms beyond that. But there is, right? Even though technically this is not a linear term, we often call this a pseudo-linear term because individually in x and y, the term is linear. Okay, so the fourth term that we're going to add is an A3xy. Okay. So compared to our linear triangle, this shape function here has one additional term that we can use for our solution. Okay. Now, again, technically that last term there isn't strictly linear because we're taking the product between two spatial variables. And whenever you take the product of two things, technically it's a quadratic term. But individually in x and y, that term still technically is linear. So, we count it as part of this. It's really the only term that we can add to this element here and still have shape complement. Okay. Okay. So that additional term here means that compared to the linear triangle, our linear quadrilateral here can account for new types of solution behavior that the triangle could not. Right? So basically, any solution behavior that depends on both x and y simultaneously, so it's changing in both the x and y direction at the same time, the quadrilateral can account for that while the triangle cannot. Okay. Good. So in that sense, at least from a solution accuracy point of view, in terms of capturing different solution behaviors, the quadrilateral just seems better, just seems superior than the triangle. Okay. And that tracks, right? And so if you think back, so I didn't really qualify this statement last week, but I did mention that if you could mesh your geometries with a quadrilateral or a rectangular type of element, then generally you can expect better solution behavior. Okay. And this kind of shows you why. So you're going to see that trend continue in the quadratic elements as well. And so generally speaking, quadratic or rectangular elements or quadrilaterals, you'll get better solution characteristics because of that additional term there. Okay. Now, sometimes it doesn't matter, right? So sometimes you're going to have a solution that doesn't depend on x, y. So let's say you have a very simple solution that only changes with x. In that situation, you don't really see a difference between the triangle and the quadrilateral because that extra term there isn't being used. Okay. So when I say that, quadrilaterals are generally superior, your solution does have to account for that, right? So your solution has to take advantage of that. If your solution does not have that characteristic, then really there's no difference. But with how complex, problems are that you typically solve with finite elements, it's very rare that you're going to have a solution that doesn't take advantage of these, I call them higher order terms. Okay. Okay. So that's the linear quadrilateral. So it's really only a difference in one term, but that one term does make a big difference. And you're going to see actually later on. So once we talk about the concept of shear blocking, that extra term there actually comes up very, very clutch. It's just one term, but it does make it. Okay. And of course, the downside to quadrilaterals and rectangular elements in general is that it is a little bit more difficult, especially for your complex geometries, to get a mesh with the rectangular. So you have to finagle with the sizes, you have to finagle with, maybe different refinements in order to get the mesh to work. But, a lot of times you're going to end up with a failed mesh, or the mesh is going to not work with rectangular elements. But if you can get it to work, then, you can kind of be more assured that your solution is going to be a better quality. All right. Any questions on this so far? Yes.
So it makes sense mathematically that because you have that extra x and y, in a lot of situations that can be helpful. How do you kind of conceptually understand that when we did the circle and the bracket, and it, like you said, it needed some of those triangles and stuff like that, because a triangle is pretty much the same as a polygonal. That extra component. It makes sense geometrically when you're looking at it that it would be advantageous to have the triangles in there. But how do you kind of explain that mathematically, given that that they're the same thing, except the quadrilateral has that extra term?
Yeah. So I explained this in the beginning. So, it depends on the character of your exact solution, right? So every problem is going to be a bit different. But, if your exact solution has a term here that depends on that extra term, then for a linear triangle that doesn't have that extra term, it's going to be impossible for it to account for that. And so it really depends on the complexity of your problem. So that's why I kind of made that statement that, generally, if you have a more complex problem, your exact solution, whatever it may be, is more likely to have these kind of higher order terms to it. And so, beforehand, you don't really know exactly what the exact solution looks like. And so, but, the more terms that you have in your shape function, you're more likely to capture more types of behavior, which leads to more accurate solutions. Any other questions on this so far? Okay, good. That's actually, let me expand on that point a bit, just because, I think it's worth talking a bit more. And so, all this talk about, accounting for different types of behavior, if you are using linear triangles, which again, there's nothing wrong, there's nothing inherently wrong with using linear triangles. There are ways to make it work, right? But, if we're making the statement in terms of, it's impossible for a linear triangle to have this type of behavior. Does that mean that you're screwed if you're using linear triangle? Not necessarily, right? And so even if your shape function does not account for a certain type of solution behavior, a lot of times that really only matters if your elements are fairly large and your solution is going to vary a lot across the element. To say, let me put it this way. One thing you'll learn about using finite elements is that most problems in finite elements can just be solved by just refining the mesh. Granted that you have enough computing power to actually do that. Okay. So to kind of illustrate this, I'm going to go back to our 1D example again, and kind of show you kind of what I mean by that. Okay. Okay. So let's go back to our 1D example here. Remember, for our 1D exact solution, we have something that looks like this. So we have 1/4 x to the fourth plus c1x plus c2. Meanwhile, our approximate solution, something like this. Okay. Where the main point of contention here is the fact that our exact solution has that x to the fourth term, right? That we say it's impossible for our approximate solution to account for. Okay. Okay. But so, one aspect of solution accuracy, has to do with this fact, right? It has to do with the fact that, your approximate solution has to have terms that are at least similar to what you expect in the exact solution, right? So that's one aspect. The other aspect is, how long or what, what I should say, what span that you're going to be performing your approximation on. Okay? So, the best thing that our approximate solution has that can approximate that x to the fourth is our x squared term. Okay. X squared is not x to the fourth, but it can imitate x to the fourth over short intervals. Okay. All right. And so to illustrate this, we can just simply plot it, right? And so if we have just a simple XY plot here, okay. So on the one hand, I'm going to plot x squared, right? So x squared is our classic, parabola. So x to the fourth, if you actually plot it, does actually look like a parabola as well. The only difference is that it grows, much more quickly than our x squared, right? And so our x to the fourth, would look something like this. Right? And so if you were to continue this graph, right? So if we were to continue this graph for higher values of x, then the deviation between x squared and x to the fourth is just going to grow, right? But if we just focus on just the area near the origin here, we can see that x squared and x to the fourth are, somewhat close to each other, right? So there is a deviation, there is a difference, but x squared does a pretty decent job of keeping up with x to the fourth over that very short interval. Okay. All right, so that's significant because remember, remember what I mentioned earlier, that when you're solving for a finite element solution, right? The requirement for the finite element solution is that the nodal values or the nodal solutions have to match in between the elements, right? So you can think of the nodes in your mesh as kind of like, reference points, right? And then really, when besides those reference points, when you're going through the element, the deviation within the element is only governed by the shape function at that point, right? So all that's to say, right? So that the kind of the upshot for all that is that if you were to refine your mesh, right, and if you were to make the size of your element smaller, then the differences between, an approximate solution and maybe an advanced exact solution tends to go down. Okay. So the smaller your elements, the less approximating you can say that you have to do. And so your solution just ends up being more accurate. Okay. Which circles back. And so, it's all kind of circular reasoning here. We kind of keep coming back to the same point, right? It goes back to the notion that, if you make your elements smaller, right, your mesh smaller and the number of elements increases in your mesh, then you can expect a more accurate solution, which is kind of what we have been talking about, for the first activity, right? Right, but hopefully that gives you a little bit more context in terms of why that actually is, at least from a function approximation point of view. Okay. But of course, the downside of using smaller elements is that you do increase the cost of your simulation. And so you drive up that element count, it's going to take longer for your simulation to finish. Which again, for this class is not something that you'll really kind of experience just because the problems we're going to be doing are all relatively small. But if you are, the difference between 1,000,000 and 5,000,000 elements is actually quite large. And so that's something to kind of keep in mind. So you can't just, sometimes it always happens at least once, mainly for activity 2, strangely. There's always someone that tries to just really refine the mesh, to be as small as possible, and you end up just crashing your computer. But try not to do that too much. Okay. Okay, any questions on this before we move on to quadratic elements? Okay, all right, so let's go over the 2 quadratic elements. We'll talk about shear locking. We'll take a break, and then we'll do ANSYS activity 2. Okay. Okay, so let's do the quadratic triangle first. Okay. Okay, so the quadratic triangle still has a triangular shape. Okay, And so we're going to have its shape function as well. So let me write out, let's do this first. Let me write out the shape function. And then, we'll go back to the element shape because we're not actually quite done with the element shape here just yet. Okay, so the shape function looks like this. And so we have A0 plus A1x plus A2y. Okay. So our shape function here starts the same way as our linear triangle, right? So we have to capture basically all the same characteristics of the linear triangle, but we're going to add some additional terms on top of this to account for other types of solution. Okay, so those terms are the following. So first we have the cross term. Okay, so first we have the term that the linear quadrilateral had, which is the A3xy. Okay, so anything that depends on both x and y, we can capture that with our quadratic triangle. Okay. And we're going to add the quadratic terms in x and y. So we have A4x squared and A5y squared. Okay, so that's our shape function for the quadratic triangle. Okay, so we have 6 terms. All right. So you might be asking yourself, how did we come up with 6 terms here? Because our triangle, still only has 3 vertices, right? And so, what we said earlier was that there's a requirement that the number of terms in your shape function has to match the number of nodes in your element. Okay. So that's still true. The only difference between the linear and quadratic triangle is that we actually add additional nodes on the element. Okay. And where those nodes are, so you might be thinking, how can we add additional nodes here and still keep it a triangle? Well, we can add additional nodes along the edges in between the other nodes. Okay. So for instance, we can add a node here, we can add a node here, and a node here. Those would be 4, 5, and 6. Okay, so those 3 nodes that I added there, those are known as mid nodes. So mid nodes are valid nodes, just like the corner nodes. Okay, and so just like the corner nodes, these solutions are required to match there in between the elements. Okay, and so you can see there's a bit more work to do with the quadratic element, but we have these additional nodes there as well. Okay. Now, mid nodes are a bit different in that mid nodes are, unlike the corner nodes, they're not used to determine the shape of the element. They're really just additional nodes that we had just to increase our shape function. Okay. But we have to include them, otherwise, we'd be stuck with the original 3 nodes, and we can't make a quadratic function with just three nodes. So we have to add the mid nodes in order to account for them. Okay. Okay, so you can see, right away that our quadratic triangle here has much better solution characteristics than the linear triangle. Okay, so we have these three new terms here. Okay. Now, remember that using quadratic elements technically is more computationally demanding than a linear element. Okay, so those extra terms there aren't free, so you do incur an extra cost. Okay, in fact, when you talk about increasing the accuracy of your finite element simulation in general, right? There's 2 types of refinement that people typically talk about. Right? And so when you do make the transition from linear to quadratic elements, or let's say that you just choose quadratic elements from the beginning, right? Technically, we call that a refinement. Where in this context, refinement refers to basically increasing the cost, or we're making a decision to increase the cost of our finite element simulation in order to obtain more accuracy. Okay. Now, when people say refinement, people generally refer to, the size of the elements, right? And so that's kind of what we use it for in activity one. We refine the elements around the hole to make them smaller in order to get more accuracy in the stress calculations there. Okay. But technically speaking, you choosing a quadratic element also counts as refinement. And so, the specific terms or the specific ways that that they're referred to in the literature is you can either have what's called H level refinement or P level refinement. So these are just fancy ways of saying, so an H level refinement, all that basically just means is you're making the elements smaller while keeping the order still the same. Whereas P level refinement is the opposite. So P level refinement means that we're increasing the order, but keeping the size of the elements the same. These are kind of old terms, and so I don't know how many people still use these terms, but in case I do see these on the ANSYS forums occasionally. So there are some old heads that work at ANSYS that still use these terms, and so I do want to introduce them to you just so that if you're reading a post or something like that, you're not lost. But this is kind of what they refer to it. Okay. So it gets these terms because H typically, when you're talking about element size, that often is given the variable H, H being kind of the edge length of the element itself. That's kind of an old way to kind of think about it. Whereas P stands for the polynomial quarter. Right? So P stands for polynomial. And so that's kind of how they obtain these terms. Again, I think most days nowadays, most people just call them element size and element order. But if you do read a paper and they refer to this, that's what they mean. Right? So it's nothing fancy. It's just, one changes the size of the elements, the other just changes the element. Okay. So moving from a linear triangle to a quadratic triangle, we are expected to get better accuracy just by the addition of those additional terms. Okay. All right. Any questions on this? Yeah.
So for the sake of continuity, does the extra nodes kind of help like the next kind of element can kind of touch where
Yeah, so basically whenever you have a node, it's a requirement that any element that shares that node has to have the same solution right at that code. So you have more nodes, you have more, I guess, reference points in between these. Okay, so let's go over the quadratic quadrilateral. Kind of a tongue twister there. Although we've talked about so much about this, there's not much else to say. But we can at least appreciate the quadratic quadrilateral for what it is in terms of having the most nodes out of all the elements of. Okay, so let's start with a quadrilateral element. So we have our four sides here. We have our corner nodes, 1, 2, 3, 4. Okay. And just like the quadratic triangle, we're going to add a mid node on each of the edges here. 5, 6, 7, and again, the exact numbering convention doesn't matter. And so, if you're OCD about it, you can go counterclockwise and count up to 8. The point is, for the quadratic quadrilateral, we have 8 nodes here. Okay, that means our shape function can have 8 terms. Okay, which is our most comprehensive shape function to date. Okay, so let's go ahead and build this up. So we start with the constant and linear terms. Right, so the first 4 terms there were present in the linear quadrilateral. Okay, so we can't leave those out. Linear behavior is still important in order to have a complete solution. Okay, so that's one thing with these elements that maybe you might be thinking, can we skip some of these terms? Because we can, thinking about it, we can achieve any polynomial order that we want if we skip some, right? Turns out you can't do that, and so in order to have a mathematically feasible solution, you need to include all of the lower order terms. And there's a lengthy proof associated with that, but that's not something that's I want to get into in this class. Okay, so we have to start with all the lower order terms. Let's add the next 2 quadratic terms. So the next 2 terms are shared with the quadratic triangle. Okay, so we have a4 x squared, a5 y squared. Okay. So those are the simple quadratic terms. Okay, so just simple x squared, y squared. Okay. So now we have 2 more terms that we can add. Okay, for nodes 7 and 8. And we're going to do basically the same trick that we did with the linear quadrilateral, is that we're going to add some additional cross terms. And so terms that depend on both x and y. And so technically these extra cross terms are not quadratic just because they're the product of 3 variables. But individually, they are going to be quadratic. Okay, so first we have a6 x squared y, and a7 x y squared. Okay. All right, so we have 8 terms here, and so basically, if your solution varies, any kind of quadratic way in the x in 2 dimensions, the quadratic quadrilateral will pick it up. Okay, and even if your solution has characteristics beyond this, and so let's say you have your solution depend on x to the 4th, just like that 1D example that we've been kind of carrying along with it. With all 8 terms here, you're more likely to get a more accurate picture of that than using any other element. Okay, good. So this is the quadratic quadrilateral. So this is as complex as it gets in 2D. Tomorrow we're going to start to go over 3D elements, and then it gets even more complex than this, although all the same concepts still apply. So just to kind of give you a preview. Okay? So the most complex 3D element in terms of shape function that we're going to look at is the quadratic hexahedron. Okay. And the quadratic hexahedron, it has 8 corners because it's a box, and then there's also a mid node in between each of the edges. And if you count the edges on a box, there's 12 of them. And so the quadratic hexahedron will have 20 terms in its shape function. So we'll look at that tomorrow. You might be thinking, how the heck do we get up to 20 terms? Well, remember in 3 dimensions, we also have z that we need to account for as well. So, there's that z component. So that's going to add some terms. And basically every combination of x, y, and z, will have to be included as well. Okay. So, even though we're still limited to a quadratic function in 3 dimensions, when we bring in z, you're going to see it gets actually very easy to get it. Okay. But that 20 terms also shows you just, how expensive a quadratic hexahedron actually is. All right, any questions on this? Yeah.
So yesterday when we did the refinement around the circle, we just changed the size, and that was basically an H12 refinement, whereas this is the people.
Correct. Yeah. 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 So H refers to the element size, P is for the polynomial order. All right, one last concept before we take a break is I want to talk about shear moment. Okay, so all this is great here, right? So we've gone over all the basic element types in 2 dimensions, and we've seen what that shape function is, right? We have kind of a vague understanding in terms of why that's beneficial, right? But there is actually one very concrete case in terms of why that is, which is the idea of shear moment. Okay. So if you remember last week as well, what I mentioned was that, if you're using ANSYS, you're using a commercial software, which makes it very easy to make a quadratic element. There's most of the time there's really no reason to pick a linear element for a structural simulation. And so this will kind of give you another reason for. Okay. So shear walking is a very specific scenario that can happen specifically for structural type simulations. All right, so if you recall from last week, when we're running a structural simulation, the primary variable, meaning the variable that's solved for first in our finite element solution, is the deformation or the displacement. So the first thing that's computed when we do our finite element solution in structure is the displacement. And then every other output or every other quantity that you can view in a structural simulation is all derived from the displacement, okay? Or deformation, displacement, deformation. I use those terms interchangeably. Okay. So one quantity that is computed from the displacement is the strain. In fact, the strain and the displacement are very closely related. Strain is just the spatial derivative of the displacement. Right? So in order to get strain, right, we take our displacement, which is a vector quantity, and then we take the derivative with respect to space, which has vector components as well. Okay. Okay. So that's pretty basic, right? So that's kind of what you remember from your solid mechanics class. Okay. And then from the strain, right? Remember we talked about this on Thursday in terms of material properties. We can compute the stress, right? So stress is nothing more. And so if we assume just an isotropic linear elastic material, the stress is simply just the product of the strain and the Young's modulus. So I know that there's more complex relationships and if plasticity is involved, and it's not as simple. But if we just look at the simplest case, right? Stress is just Young's modulus times strain. And even if you have something more complex like a hyperelastic material, Stress and strain are always going to be closely related to each other, right? So stress is computed from the strain. Okay. Now, what's unique about the structural mechanics equations is that the stress is not something that is just appears in the post-processing. The stress is actually part of what's used to compute the displacement. And so this is kind of a loop here. Right? And so stress actually comes back up here because stress is used to compute the displacement or deformation. Okay. So the governing equation for structures is unique in the fact that the stress appears explicitly within the equation itself. Right? It's not the only differential equation that does that, but it's the one where it appears just so explicitly, right? And physically, it makes sense too, right? And so, if you think back to activity one, right, we applied our tensile force or tensile pressure on our plate, right? And what we saw was that the entire plate deformed in response to that boundary condition, right? And so the way that that force propagates through the entire plate, right, it does so by the stress, because when you apply that force at the end, right, that's going to cause some stress, locally near the force, and then that stress is going to propagate to the left all the way through down to the fixed support of the plate, right? And so you have this phenomenon where stress drives the deformation in throughout the entire structure. Okay. Okay. So all of that makes intuitive sense, right? So that's kind of what we understand from solid mechanics. But there's one part of this entire process here that really depends on, that really can be affected by our finite element choices, which is the middle choice here, or the middle part. Okay. The computation of the strain. Okay, so the strain, we know that the strain is the derivative of the displacement, right? Now, what do we know about the displacement from finite elements, right? When we're doing finite elements, we are assuming a form of the primary variable, right? So even before we start running a structural simulation, we've already assumed that our displacement is going to have a certain functional form. Okay. And so more specifically, right, if we look back at our discussions of our element orders, we can either assume that the displacement is going to be linear or it's going to be quadratic. Okay. So something strange happens when we choose a linear element. Okay. So I'm going to focus on that. Ooh, that's ugly. Red highlighter on yellow on red. Okay. So what happens when we have a linear solution, right? When you take the derivative of a linear function, what do you obtain? You obtain a constant, right? Right. All right, so you take, if you assume the simplest linear solution, and so if we assume 1D, we assume our solution is A0 plus A1x. We take the derivative of that with respect to x. We just end up with A1, which is just a constant. Okay. And so if we follow that along, right? And so if we follow that along kind of our logical pathway here, that means for a linear element, the strain within the element within a linear element is also going to be constant. Right? A strain is just the derivative of the displacement. And if the displacement is linear, that means our strain must be constant. Okay. And if our strain is constant, that means our stress is also going to be constant within an element. Okay. So it's kind of a chain of events that kind of, just keeps kind of cascading. Okay. And so that last statement there is actually pretty significant. Okay. And so what it means then is that if we have a linear element, then when we compute our stress, within each element in particular, the stress is not going to change, right? And so we have basically constant stress elements. Now, when you go from element to element, the stress may change, right? So it can hop at that point. But within an element itself, the stress is going to be constant. Right? Which by itself is not a bad thing, but if you think about how our structural equation kind of works, where the stress is computed and it's used to compute the displacements, right? When you have elements that have constant stress, you're not going to see a difference in stress when you go from one end of the element to the other, right? And so when that happens, when you have a state of constant stress, you don't really get any deformations within that element itself because there's no differences in stress. Okay. And so what then happens is that, when you have elements with constant stress, the deformations that you compute end up being much, much, much smaller than what they should be. And so when you have constant stress elements, what tends to happen is that this severely underestimates the deformation. Right. And so, if you have shear locking that's occurring, then, your deformation is going to be severely underestimated, which visually, if you look at your structure, it almost looks like the structure is kind of locking up on itself. Right? And so if you have shear locking, it doesn't matter how much you increase the forces, how much you increase the loading, your deformations are always going to be very, very small. Okay. And so this type of phenomenon where the structure looks like it kind of locks up, they've called this shear lock. Which is bad. You don't want shear locking to occur. Okay. So you're not going to so sometimes people ask can we see shear locking in ANSYS? ANSYS actually does do a lot of advanced stuff. So even if you use a linear element, it's actually very hard to get shear locking to occur because ANSYS actually adds a lot of safeguards. But if you're using kind of a naive kind of finite element solver, this is something that you would see. Okay. Now to solve for shear locking, there are a couple of things you can do. And one of them is either just refine your mesh or just use quadratic elements. So anything that just adds any kind of refinement to your mesh, to your simulation, most of the time that's going to solve shear locking. So shear walking, it is something, it is a very interesting phenomenon. It is kind of a thing of the past just because, a lot of modern softwares will account for this. I think ANSYS there's actually a warning message that ANSYS gives. If ANSYS detects that the deformations are too little, it'll warn you and tell you to refine your mesh. Okay. You really have to have a very coarse mesh in order to observe shear walking. And so if you have, if your mesh is fine enough, even moderately fine, you're not going to observe it. And so it is actually kind of hard to recreate, especially for the simple cases that we're looking at. So this is kind of something that's a thing of the past, but I think it is a very interesting application of kind of what we've been discussing in terms of element size, element order, and how that affects your results. Okay. All right, any questions on this before we head for break? Okay, all right, so let's take a break. So let's come back. Let's come back 4:32, and then we'll start ANSYS activity 2. Okay.
Professor, I was looking on the syllabus and said that there would be virtual labs for ANSYS. Is that still accurate or no?
Oh yeah, I need to probably remove that. That was an experiment that was a few years ago, but yeah, it's not active anymore.
Gotcha.
Yeah. Yeah, so if you're gonna use ANSYS at home, just I would say just download the student version.
Okay.
It's computer. It is pretty heavy. I had to reinstall it recently.
Mhm.
And I had to uninstall quite a few games from my laptop.
Yeah, no, it's like a 20 gig thing
Yeah.
on zip.
Yeah, it's a lot.
And so like, I was able to get on my computer, but let's say like in an emergency, like in a snap, I need to use ANSYS on a different computer. Are there labs available on campus that I
Yeah.
can do? Yeah.
So I think it's in the library as well.
Okay.
Any computer that's in the ECS college will have ANSYS as well.
Oh, okay.
Yeah. All right, it's 32, so let's get back to it. Okay, so second half of class today is going to be ANSYS activity 2. So ANSYS activity 2 is going to be quite a bit less hand-holding than activity 1. So activity 1 was kind of our first experience with ANSYS. Activity 2, I'm going to let you kind of explore ANSYS a bit on your own. I'm going to let you guys make the decisions in terms of things like the meshing, the boundary conditions to an extent. You do have to have certain characteristics, but I'm gonna let you guys decide how to apply them, and then do the analysis yourself. Okay. So activity 2 is nice. We're kind of past the state. I mean, it's crazy to say that just because we're in week 2 this summer, but it goes so fast. We're past the stage of introducing the basics, and now we're getting to more of the applying. Okay. Okay. So let me go ahead and share my podium computer here. Okay. So the starting point for this, and so I did post the assignment page for ANSYS Activity 2. And so if you go to the Canvas site, you click on ANSYS Activity 2. There's a few files for you to download here. So first of all, there is the PDF, which has all the instructions and the activities. And so that's here. So we'll be going over kind of the first half of this together. And then there's CAD files to download here as well. So there is a CAD file for the bike crank, which is what we're going to use for the activities in class. And then there's one other CAD file for a bike frame, which is going to be a something you do for the home. Okay, okay, but we'll go through the first part here. Okay. So before I kind of start talking about this, let's go ahead and launch Workbench, just because we know that it takes a while to open up. Okay, so I'm going to launch Workbench. The version I have here on the podium is 2025 R2. But you guys can just, if you're working from one, you'll probably have 2026 R1. For this activity, they're going to be the same. Okay. Okay, so I'm going to launch that, and then let's talk about the context for this activity. Okay. All right. So activity 2 is going to be our first kind of exposure to using ANSYS to actually do something useful. Okay. So in activity 1, we did the simulation on the plate with a hole. It's a great introductory activity, but not very physical, or not that kind of applicable to the real world. So in activity 2, we're going to be actually answering an important question and using simulations to account for it. Okay. Okay. So the situation is the following. So we're basically in charge of designing a bike frame. So if you're not familiar, it's the part of the bike that connects to it attaches to the pedal, and it causes the the gears to turn, it causes the wheels to turn. Okay. So it's just one small component of the entire bike. Okay. And ultimately, what we're interested in is taking this current design and finding out, the maximum amount of force, maximum amount of load that it can handle before the bike crank will start to fail. Okay. So we'll actually also be applying, a lot of the knowledge that we gain in terms of solid mechanics here. So, we'll be computing the von Mises stress. We'll be comparing that to the yield strength of the material itself, and using that to determine if the bike crank is going to fail. Okay. So unlike the previous activity, we're going to be importing our geometry, so we're not going to be drawing it from scratch. And so that'll actually save us quite a bit of time. And we're going to be implementing a custom material as well. And so we're going to make the bike crank out of aluminum. And I'm going to show you a couple ways that you can implement that, because aluminum is a very common material, and so ANSYS does have aluminum that's built in. But I'm going to show you how to add the material properties manually as well. Okay. Okay. So with that, we can go ahead and bring it up on my iPad here so I can follow along. Everyone was able to open up Workbench and have downloaded all the cat files for the activity. Okay. All right, so let's go ahead and get started. So we have Workbench here that we've opened up. So just like activity 1, we're going to be running a static structural simulation. So let's go ahead and click static structural and then drag it into the workspace here. Okay. All right, so that's going to create our static structural menu here, and we'll be working off this for the activity just like activity 1. Okay. Okay, but unlike activity 1, we are going to start with the engineering data. Although I guess technically I did show you guys this last time. Okay, because we need to add our material. Because unlike the first activity where we just use the built-in structural steel, we need to add aluminum to our activity here. Okay. Okay. So into Workbench, let's go to engineering data and let's double click it. Okay, so double clicking engineering data will open up this new menu here. Okay, which will list all of the materials that we have currently loaded into our product. Okay, so by default, ANSYS only loads a single material, which is structural steel. Okay, so that's the material that we use in activity 1, and the properties for structural steel are given by this table down here. Okay. Okay. But for this activity, we want to add aluminum, right? And so there's a couple ways we can do that. And so we can use the built-in aluminum that's within ANSYS itself, right? And so if you have a fairly common material, this is generally what I recommend, just so that you can avoid kind of making mistakes when you're typing in material properties, which happens more often than you think. Okay. So to access ANSYS's library of materials, you're going to go to click on this button right here. Okay. So the button's called Engineering Data Sources. Right, so go ahead and click on that. Okay. So that's going to open up a new menu here, and we're going to look first at this box here that says Engineering Data Sources. Okay. Now, depending on your ANSYS, this box may be in a different spot, especially if you're using the computers here in the lab. People like to move these around, and then ANSYS saves where that location is. So for me, it's at the top here, but this box here might be somewhere else in your GUI. So just be aware of that. But what you should see in this menu here are the different types of material libraries that ANSYS has. Okay, and so there's ANSYS Granta, so that's kind of their big kind of library of materials. Big scroll here. We have general materials, we have additive manufacturing materials, geomechanical materials, composite materials, nonlinear materials, magnetic materials. So there's a lot of options here. Okay. We're going to go under general materials first. Okay. Just because aluminum is as general a material as you can get. Okay. So you're going to left click on general materials once, and then in this new menu here, okay. So the menu should be called Outline of General Materials, which again, this box may be in a different spot depending on your ANSYS GUI, but hopefully it's somewhere that you can see. Okay. We're going to scroll around here and we're going to add aluminum, right? And so if you scroll up to the top, you're going to see that there is an option for aluminum alloy. Okay. So let's go ahead and add that to our project. And so to add a material to the project, you're just going to click on this plus arrow. Okay. And so after you click on that plus arrow, you should see that there is going to be a book that's next to that material. Okay. So that tells us that we've added that aluminum alloy material to our project. And if you scroll down a bit, you can see that there's structural steel here as well. And structural steel already has that book because that's the default material. Okay, and so if you go back to our engineering data, so if we basically click on this engineering data sources button one more time to close that, okay, you can see now that we have 2 materials that are added. So we have our structural steel, which was our default material, and then we have our aluminum alloy here, which is the material that we just added through the library within ANSYS itself. Okay. Okay, and then you can left click on aluminum alloy here and you can check the properties here down as well. Okay. Okay, any questions on that? Everyone able to add aluminum alloy through the ANSYS material library? Okay, good. Okay, so I would say, if your material is fairly common, I would look through the library first to see if it's there. Okay. Especially for your midterm projects, and so that's definitely a great option. But let's say that you wanted to add a custom material, right? So maybe there's nothing in the library that fits your needs, or maybe your aluminum has slightly different properties than the library one here. We can add a completely custom one here. Okay. So to add a custom material, we're going to click here. And so if you click on this empty box underneath structural steel, you'll see the text there reads, click here to add a new material. Okay, so let's go ahead and click on that. It's going to allow us to add a name for this material. So let me call this aluminum. And in particular, we are aluminum 6061 T6. Okay. Doesn't really matter what you name it, as long as the name is distinct. So don't call it aluminum alloy because we already have that name taken. Okay. Okay. So now we have this new material that we've just created here, but we haven't added any material properties. Okay. You go back to our project specifications, you can see that this aluminum 6061 is going to have a Young's modulus of 1 times 10 to the 7th psi and a Poisson's ratio of 0.3. Okay. So we need to add those properties to our new material here. Okay. So to add properties to a material, you're going to go to the toolbox that's on the left-hand side here. Okay. And there's a lot of different material properties that you can add. Okay. So if you think back to our lecture on material properties, you'll see here that there is, you can add linearly elastic material. So there's isotropic elasticity, orthotropic elasticity, and anisotropic elasticity. Okay. You can add hyperelastic material properties. And so these are all the hyperelastic material models that ANSYS has built in. You can add plasticity, right? And so these are the plasticity terms that we talk about. So there's our bilinear, bilinear type of plasticity there, right? So there's a lot that you can add. And you can add things like density as well here. So that's the physical properties. Okay? But for our purposes here, we only need to add the isotropic elastic material properties because that's all we're given. And so we're only given the Young's modulus and Poisson's ratio. And so the fact that we're only given these two means that we have to assign this as a linear isotropic material. Okay. Okay, so let's do that within ANSYS itself. Let's go back to Workbench. Okay. And so to assign the isotropic linear elastic materials, you're going to click and drag isotropic elasticity. Okay. And you're going to click and drag that onto our new material here, the aluminum 6061 T6. Okay. Okay, and so after you click and drag the isotropic elasticity on there, okay, on the bottom portion of the screen, this is going to give you a chance to add in the material properties for that material. Okay. And so you can see here there's a box for the Young's modulus and there's a box for the Poisson's ratio. Okay, so let's go ahead and input both of these. So let's start with the Young's modulus. And so the Young's modulus is given to us as 1 times 10 to the 7th psi. Okay. Be careful of the units here. And so remember the Young's modulus is given to us in psi. So let's make sure our units are going to match that. Okay. So we go into Workbench here. We look at the Young's modulus. By default, the Young's modulus is being defined in Pascal, which is the SI unit for Young's modulus. But we're not giving it that. We're giving it our Young's modulus in terms of psi. So let's make sure that we switch the units to psi here. And then now let's input the Young's modulus, which is 1E7, which is 1 times 10 to the 7th. Okay. And then we have to input the Poisson's ratio. Poisson's ratio is pretty easy. Poisson's ratio has no units. And so we're just going to put 0.3. Okay, so that's two different ways to add a new material to your project. You can either add it through the built-in ANSYS library, or you can define it yourself, using the way that we just talked about here. Yeah. Any questions on this so far? Everyone able to add that material? Technically, for this activity, you only need one way. So if you just have the aluminum alloy, that's fine. Okay, good. Okay, so we're done with the material properties here. So let's go ahead and exit out of this. And so to return back to our project workspace, we're going to exit this tab. Okay. So the tab for engineering data is up here, and so we're just going to click on this X up here. Okay, so that's going to bring us back to this menu up here. Okay, so now let's deal with the geometry. So for activity one, we drew our geometry from scratch, and so we made a sketch, we made a hole, we essentially extruded our geometry and we ran our analysis from there. So it's very much kind of like a SolidWorks kind of built it from scratch. Okay, that's not the typical way that ANSYS is used. And so even though you can create CAD models within ANSYS, that's definitely not ANSYS's expertise. And so a lot of times, you're going to be generating your CAD file outside of ANSYS, and so you'll be using SolidWorks for the most part. And you can also use CATIA for those of you that are taking 422 or have taken 422. Okay. You do have to convert the file, and so you just can't import a SolidWorks part just raw like that within ANSYS. And so you do have to convert it to a file format that ANSYS can read. But generally you want to be importing your geometries. Okay, so to import a geometry, you're going to right-click on geometry from the workspace here. Okay. You're going to go to import geometry. And then you're going to click on browse. Okay, so that's going to allow you to browse your file system and import a specific geometry file. Okay. Now to get the geometry file for this activity, that is posted onto Canvas right now. And so the one that you're going to need for the in-class activity is the bike crane. Okay, so make sure you download that. Okay, so the name of that file should be crank_assembly.x_t. Okay. So let's go ahead and import that in. I was testing it earlier, so it's here, but yours probably doesn't have this. So let's go ahead and click browse. Let's go ahead and navigate to the folder which has it, which for me is in the downloads folder. And this crank_assembly is the file that we have. Okay, so we can double click that and it should import pretty easily. Okay. Now, before we jump into mechanical, let me talk about the file format just briefly. If you were interested in using ANSYS together with SolidWorks. Okay. Now, because we have SolidWorks installed on this computer here, it's going to show that this file here is a SolidWorks file. Okay. But if we right-click it and we click on Properties, you'll see that the file extension is actually x_t. Okay. So that file format is actually called Parasolid. Okay. So Parasolid is one of the universal, I would say, CAD file formats that's kind of designed to work in other types of programs. And so if you have SolidWorks, you can export one of your parts or assemblies into a Parasolid file. And so you would definitely need to do that if you wanted to use ANSYS with it. Okay, I believe CATIA also has the same functionality. Other types of file formats that can work within ANSYS, a very common one is a step file. And so that's .stp or .step for step. Okay. And so SolidWorks should be able to export a geometry file in that format as well. Okay. Another common one is an IGS file, so that's .igs or .iges. Okay. Okay. So that's another very standardized CAD file format. Okay. And so just be aware that if you want to use ANSYS with one of your pre-made CAD files that you've maybe already generated, maybe you're on a senior design team and you've already CAD'd up some parts. And so if you want to import it into ANSYS for analysis, you do have to convert the file format into one of these files. Okay. Okay. There is another file format that's often used in ANSYS called an STL file. I wouldn't recommend STLs. STLs don't really have a lot of information with it, and so it could be sometimes hard to identify surfaces and run the simulation from an STL file. But sometimes that's all you have, especially if you're 3D printing parts. I think STL is the standard file format for that, and so it can work. It's just that you may have to do a little bit of extra work in order to prepare the surface. Okay. Okay, but I just wanted to make that aside, just because from now on, we'll be importing our geometries. We're not going to be drawing them anymore. Okay, so I'm gonna go ahead and open up ANSYS Mechanical, right? And so now that our geometry is imported, we can go ahead and double click on model to start ANSYS Mechanical, okay? And while ANSYS Mechanical is opening up, are there any questions about the geometry import or how that works? Okay, good. Okay. So for most 3D simulations, you're going to be importing your. Okay, so it always takes a minute or two for ANSYS Mechanical to open up, but thankfully this is going to be the last program that we have to open up. Okay. So in the previous activity, we had to open up Design Modeler in order to draw our geometry, but since this time we're importing it, we can just jump straight into Mechanical and do our mesh and boundary conditions from. Okay. Okay, so if everything turned out well with your geometry import, you should be able to see the part here. Okay, so here is our bike crank. Okay. Technically, it's an assembly, so it's an assembly of actually 3 different parts here. But we're going to focus our analysis just on the crank portion. Okay, so is everyone able to open up ANSYS Mechanical and you see the part opened up here? Okay, good. Okay, so first thing we're going to do is we're actually going to suppress some parts of this assembly. Okay. Now this happens very often because a lot of times when you are preparing a CAD file, right? So you are CADing something up in SolidWorks or CATIA. Oftentimes you're including all these different details in the geometry just because you're either going to be manufacturing those parts or it's going to be part of the final drawings. But for the analysis, we only really want to focus on the parts that are going to be essentially load bearing. Okay. Every other part of your simulation or every other part of your CAD file, if they're not going to be contributing to the structure of the simulation, then it's often best to suppress them because we often don't want to waste mesh elements on kind of useless parts of our geometry. Okay. And so for this particular case, if you look back at the project specifications, we're really only interested in the crank portion because that's the only part that we're concerned might be breaking. Okay. And so if we look at the CAD file here, we actually have a pedal that's included as well as this fitting ring that kind of makes sure that the pedal fits with the crank here. And probably also lets it rotate as well. Okay. So we don't need these 2 parts, and so we can go ahead and suppress them. Okay. So to suppress a part of the assembly, you're going to go to the left-hand side of the screen. Okay. There is a menu here for geometry. So let's go ahead and click on the plus arrow here. Right, and so after clicking on the plus arrow, you can see that we have 3 components or 3 parts of this assembly. Okay. There is the bike crank itself. And so if you left click on a part from the menu here, it will highlight in the screen here to show you which of that part is. Okay. Next, we have the pedal, which is this kind of cylindrical part here. And then we have this kind of fitting ring, which doesn't really have a good name. So it's called part 9 SM2 Rev by 375. Okay. Okay, so we don't need a pedal and we don't need that ring there. And so let's go ahead and suppress them. Okay. So when you suppress a part in your assembly, you're basically excluding it from the analysis. Okay, so we're not going to compute a solution. Right. And so to suppress it, you can right click on a part in the assembly and you can click on suppress. Okay. Don't delete it because we might need it later. Okay. And don't hide it. And so if you hide a body, it'll still technically be part of your analysis. It's just that the visibility will be taken out. Okay. But we actually want to suppress it out so that we don't, again, we don't waste any mesh elements on that one thing. Okay. Okay, so we can go ahead and click on suppress body. So it's going to suppress the pedal. Okay. And then we can suppress this ring as well. So once again, on the part 9 SM2, right click and click suppress. Okay. Alternatively, if and for this activity, not that useful just because we only have 3 parts. But if you're going to be suppressing a lot of parts, right? Another way you can do is if you know which part that you're going to focus on, you can right click on the part and you can click on this button here for suppress all other blocks. And so that suppresses everything else as well. Okay. And so next thing we're going to do here is that we also need to assign the material properties for this part as well. Okay. So by default, right? And so if you left click on the bike crank here, you go to the bottom left-hand side of the screen. By default, the material for this part here is assigned as structural steel. It's just because that's the default material in ANSYS. But we know from the specifications that our bike crank here is actually made of aluminum. Okay, so let's click on this arrow. And you can see the different materials that we've added to our project. And so we have the aluminum alloy. So that was the aluminum that we loaded in manually, or we loaded in automatically from the ANSYS material library. And we have the aluminum 6061 T6, which was the custom aluminum that we added in, where we input the Young's modulus and Poisson's ratio more directly. Okay. So for this one, it doesn't really matter. They are actually slightly different from each other. I actually forgot to kind of check that. But they are very similar. Okay, so aluminum is aluminum. So I'm going to click on aluminum alloys because that's the one that's within ANSYS itself. But feel free to kind of choose whichever one that you. Okay. As long as you're one of the aluminums that you're not structural steel. Okay. Any questions on this so far? Yes.
Is there like a Command Z or like a go back option on this? Like if I do click something wrong, can I undo?
Yeah, Control Z should work.
Is it okay?
It probably works for the meshing qualities here. It's been a while actually. Let me search it actually. Undo. Yeah, so there it looks like there is an undo option here. I think it probably depends on the type of action. Okay, I saw there's a question in chat. Okay, good. Okay, good. Okay, so that's all the new stuff with this activity. So from this activity, we learned how to add a custom material. We learned how to import a geometry here. Okay. From here, it's the next step is the meshing. So if you go through the activity here, you go down to page 5. Okay. There is a meshing problem. Okay. So we've talked about meshing quite a bit in this class already, right? So we talked about the basics last week. We talked a bit more today about the meshing. Okay. So you should be fully equipped to be able to choose the mesh yourself. Okay. So I'm going to let you guys work on this. And so, I'm not going to give you too long just because there's not too many decisions to make. But I do want you guys to make a method object for your mesh. Okay, so remember from the method object, you can choose the shape and the order for the element. So we talked about that today. Okay. And you can make a sizing object as well. Okay, where you can define the size of your mesh elements. Okay. So let me go ahead and show you how to make those one more time. So remember to make a mesh modification object. You're going to right click on mesh, you're going to insert. Okay, first one we're going to add is a method, right? And so that's going to allow us to choose the order and the shape of the elements. Okay, make sure to apply this to the entire geometry, right? So I'm going to left click on the geometry, hit apply here. Okay, and then we're also going to insert a sizing object as well. So right click mesh, go to insert sizing. Okay, once again, you're going to apply this to the entire geometry here. Okay. And you can input the size of the mesh elements here. Remember, you can change the units, and so if you want to change the units to something a bit more convenient, mine's already set to millimeters, which is pretty good. But if you want to do the mesh in centimeters, then that's possible as well. Okay. All right, so I'll give you guys a few minutes, and so I'll give you guys maybe 5 minutes to go ahead and choose those mesh settings. And then once you're happy with your mesh, then we'll kind of go on from.
For refinement,
Wait.
do we do it around the circles as well? We do the edges and we just refine around those. Yeah.
You could. But remember, refinement is mostly for regions where you're going to expect the stresses to concentrate.
Okay.
And remember, you only really want to add the refinement in those cases where you have those sharp solution gradients. And so, it's a little bit hard to tell at this point, just because we haven't talked about the boundary conditions. We haven't looked at the results. So I wouldn't worry about refinement just yet. And so I would just focus on just the method and the sizing.
Okay. Thank you.
Yep. Our question.
So it's too dumb.
Oh, good question. Yeah, so Jason brings up a good point here. So actually, if you left click on mesh here, there is a way for you to actually change the size of the elements from here. And so if you go under defaults, there is an element size option. So you can actually change the size of the elements here as well. So you can do that for this activity just because we're applying just one size for the entire mesh. Okay. So that's essentially what this is going to do. But by creating mesh sizing objects, in later activities, you're going to see that this is going to allow us to change the size for different components of the mesh. And so for now, I would prefer that you make the meshing, the body sizing object, just to kind of get in the habit. But for this activity, technically you can do it from the defaults here. So. Okay, and so I'm going to make my rounds, and so in case people are having other questions, but I'm going to come back at 5:05, and hopefully you guys will have a mesh by that point. Okay, but if you're in the class, you have a question, just raise your hand. I'll come around.
That's where I need to check my. Next, other. Our rate on. Again. Once we have that check mark, we just double click on basically make it and see what we can.
Okay, all right, so it's 5:05, so let's go ahead and move on. Okay, so this is the mesh that I have here, and so you can see that I chose hexahedral elements just because those are, like we mentioned, they have a more comprehensive shape function, and so we're going to get better solution properties from there. Okay, you don't see it here, but I've also chosen the element order to be quadratic. Okay, for the sizing, there's a lot of different options you can do with the sizing, and so this mesh that I have here is fine. Okay. Again, we have a fairly simple case here, and so we don't necessarily need a ton of elements here. But you know, you should get a mesh here where the mesh elements, you know, they look fairly neat. Okay. I do want to bring your attention to one feature of this mesh though. Okay. So again, you know, meshing is something we'll continue to talk about, you know, throughout the entire summer, just because there's a lot of nuance and there's a lot of factors of the mesh. Okay. One thing I want to bring your attention to is that if you look across the thin dimension of this crank, okay, so this crank obviously is much longer than it is wide. Okay, so if you look at the dimension in this direction here, okay, the crank is pretty thin. Okay, and so there's it's a little bit difficult to pack in a lot of elements in that direction. Okay, but with the mesh size that I've chosen, okay, if you look at this direction here, so you basically travel across the shortest length or the shortest dimension of the part, right? You'll see that I've crossed two elements here, right? And so there's one element here, another element here that we're crossing. Okay. And so this phenomenon here, or this metric, is what I'd like to call elements through the thickness. Okay. And you should always aim to have at least two elements through the thickness here. Okay. Now we can adjust this mesh sizing, and so you know, if I make this mesh sizing a bit larger, okay, and so if we go back to the default, I think the default was like 11. So if we go up to like 10 or something. Okay. So I changed the mesh sizing to 10. Let's go ahead and generate the mesh again. Okay. You can see that in this scenario, I only have one element that goes through the thickness, and so that element is so big, it kind of goes all throughout. Okay. This is a situation you generally want to avoid, because what happens in these situations is that if you look at all of the nodes on this element, right? So if you look at this element here, okay, all of the nodes on this element are resting on the boundary of our geometry. Okay. And so that means that all of these nodes here are going to be subjected to a boundary condition of some kind. Okay. Now they may just be subjected to the default boundary condition, which is the stress-free boundary condition. Remember, we talked about that last Thursday. But generally, this is not very good practice. And so you want to have at least one layer of interior nodes through the thickness here. Okay. And the more, the better. And so the more elements you have to the thickness, the better quality your mesh and your solution is going to have. So let me switch it back to 5 mils or 5 millimeters. Okay, and so you can see here that now we have two elements through the thickness, which is much better. Okay, you may have noticed also that I got a warning here. Okay, and so if you look at the warning, this warning says this mesh creates a lot of internal period elements. Okay, for the most part, if it's a warning, you can generally ignore those. Warnings are just warnings; they're not going to stop you from running a simulation. And so you know, unless the warning sounds dire, you know, ANSYS kind of warns you about a lot of things. If you're ever curious, you can always just ask me. You can say, hey, I'm getting this warning message. Is this something I need to worry about? Most of the time, the answer is no. But sometimes it's yes. And so if you're ever unsure, just let me know. Just because, you know, the warning messages, they're written in a way that I think an expert would understand generally. But if you're just learning finite elements, you may not kind of understand what the warning message says. So just either email me or just flag me down in class. I can help you. Okay. But this mesh here is pretty decent, but of course you can go smaller than this as well. Okay, so next is the boundary conditions. Okay. So this is another part where I'm going to let you guys kind of handle on your own, okay? But, you know, I'm not going to let you kind of just do whatever. So there are some restrictions with the boundary conditions, okay? And so remember from our discussion last week, we know that there has to be at least one constraint type boundary condition on every simulation that we do. Okay, so you should aim to add at least one fixed support. So there should be at least one fixed support somewhere in this model here. Okay, and we'll talk in a bit about kind of where that has to be. The other restriction is that there has to be a single load here. And so the single load is going to be a 100 pounds of force. Okay. And so there has to be at least 100 pounds of force somewhere in the model. But I'm going to let you guys choose where you think it makes the most sense to apply that force and also the direction of the force as well. Okay, so for both of these boundary conditions, you have to determine where you're going to apply them, okay? And then for the force boundary condition, you also have to determine the direction, okay? So let's talk through it a bit. Let's talk through the logic in terms of where I would expect these boundary conditions to go, okay? So let's work backwards, actually. So let's work on the 100-pound force, okay? All right, and so actually, if you read the scenario, so if you kind of read the situation that we're aiming to simulate, okay, so if you go back to the project specs, okay? We are simulating a scenario where, someone is going to be pushing down on this bike crane with the force of their weight, okay? And so that's what the 100 pounds is meant to represent. And we want to apply it in a way that is going to put the bike crank in danger of failure, okay? Okay, so this 100 pounds force here, this 100 pounds force is meant to emulate a person's weight, okay? As they're trying to pedal, okay? Okay. So that's your hint in terms of where you're going to apply this 100-pound force. Okay. The other hint in terms of the direction is that you want to choose a direction that's going to cause the most stress within this bike. Go ahead, Chris.
Are you asking, or were you just telling us to take it under consideration? I didn't hear that part.
Yeah, so you're going to be choosing the location and the direction for this force, but these are the hints I'm giving you in order to determine where to apply it as well as the direction to apply it. And so we know the magnitude. The magnitude has to be 100 pounds, but depending on the direction that you apply the force, it's going to cause a different amount of stress within.
Yeah, tracking. I just didn't know if you wanted us to share where we thought it should go.
Oh, no. Yeah. So that's so I want you guys to work on that for the next 5 minutes. But these are the hints, and then we'll reconvene in about 5 minutes, and then we'll talk about kind of what you should get. But yeah, I want everyone to kind of think about it and kind of apply it himself.
Okay, perfect. Thank you.
Okay, and then the fixed support here, we have to choose the location for that, and so there's no magnitude associated with that. But for the fixed support, generally you want to pick these to be in the location where your part is going to be attached to some greater or bigger kind of object. Okay. So this bike crank is going to be attached to the bike frame. Okay. And so think about where this bike crank is attached to the frame, and then that's where you're going to apply your fixed support. Okay. Okay, so that's all your hints. Let's reconvene at 5. We'll do 5:20 just to kind of round up. And then I'll kind of show you what I would pick for these things. Okay, but think about these things. Okay. No, it's not 520. It kind of seems like everyone's kind of figured this out. Okay, so just to kind of summarize kind of what I did here, and you know, remember to add boundary conditions, you're gonna right click on static structural A5 and insert here. Okay, so we inserted two boundary conditions. So first is a fixed support, and so we're gonna fix this bike crank where it attaches to the bike frame. Okay, so if you remember from earlier, we suppressed the pedal, right? So the pedal is gonna be was on this side of the bike crank. And so the frame is attached on this side. So I've gone ahead and fixed all three of these. You technically only need one, but you can also select multiple surfaces if you want. So if you didn't know, you could click on a surface and then hold down Control on the keyboard and click and to select multiple. So I applied the fixed support on that part there. And then for the force boundary condition, I applied it on the pedal side. Okay. And so I applied it onto this kind of ring right here. So remember, we suppress the pedal, but whatever force that we apply on the pedal is going to be transmitted to the bike crank through this hole. Okay, so I've chosen that hole right there as the location. Okay, and here I have my 100 pounds of force. Right, and so remember, don't forget to change the units. Right, remember we're applying the force was given to us in pounds, and so we want to make sure that we apply it in pound force. Okay. All right, and you can see here that I've applied the force in the y direction. And so remember to change. So by default, you know, any forces or pressures is defined by a vector. But remember, generally, I like to apply things in terms of components. That gives us the most kind of freedom and flexibility in terms of the direction. Okay. And I've applied that force in the y direction. Now, technically, you can go in the negative y direction, right? And so if you're viewing this as, you know, we're viewing the pedal from the top, right, and we're pushing down, we can do a negative 100 here. Okay, so that'll put the force in the negative y direction. It doesn't really matter just because of symmetry, right? So our bike crank is symmetric on both directions there. You know, but if you want to kind of align it with your view, then that's fine as well. Okay. Now, the reason I'm putting the force in the y direction is that by doing so, right, we're going to induce a bending stress onto our bike crank. Oh, sorry, I apologize. There's a question in the chat. Okay, good. Yeah, that's right, Chris. Okay. Okay, yeah. So we'll get to the results in a second, Jason. But yeah, I'll get there in a bit. Okay, so by doing this, you know, we're applying a bending force onto our bike crank, right? So the other option that you might have had is you might have also put the force in the x direction. Okay, so you can either put a tensile or compressive force. That's what the x direction would do. But tension and compression is never going to apply as much stress as bending. Okay. So if you think about it, you know, if someone were to give you a twig and they asked you to break the twig, right, you would never try to pull the twig apart or compress the twig. Maybe if you're a psycho, you could do that. But, you know, generally speaking, if you're given a slender object and you're asked to break it, you would generally bend it, right? Because that's the easiest way to break it. Because that's the direction or that's the way to induce the most stress in a part like this. Okay. And so by applying that force in the y direction, that would induce bending. Okay. Now, technically speaking, you could also induce bending by applying a force in the z direction as well. Right, so that would be the other option to induce bending. But the z direction wouldn't really make the most sense here because a bike crank is never going to experience force in that direction. Because now no one's kind of pushing on their bike crank from the side. You're generally kind of pushing up and down on the bike crank. So in this case, the y direction makes the most sense. Okay. Question from the chat. So how do I switch the units or pounds? And so to switch the units, you're going to go to the top here and click on home. Okay. And then in the middle of the screen, after you click on home, there is a button for units. And so you can click on any of the two in the bottom here. So any of the US customary will convert the units to pounds. Okay, good. All right, so that's kind of my reasoning with the boundary conditions. Any questions on the boundary conditions from there? All right, question. So if you want to force or flip the direction exactly 180 degrees, you just put a negative in front of the force. Yes. Yeah. And so if you want to apply a force, you flip it 180 degrees, you just put a negative sign. Yeah, exactly. Okay. All right. And so that's about it. And so we're just about ready to look at our results. Okay. And so if you look back at the project specifications here, so let me go ahead and clear my doodles. right? So we just finished problem 2. And by the way, so for your activity report that you're going to submit, there are questions in these parts here, problem 1, problem 2. Okay, so don't forget to answer those as part of what you submit. Okay. Problem 3. Oh, question, yes.
Yeah, so I'm kind of thinking about the link from like a dynamic perspective, like it as a mechanism. It makes sense what you're saying that in the X direction would be the most works because it would be bending, stuff like that. And then you were saying that we chose the Y direction because of the location of as you're applying and stuff like that. It would make sense that you're applying floors. The thing is that like when the because that piece is technically a moving part, but it becomes more static near the bottom. Still outside. Would it be wrong to assume that it's just in the X direction?
No, it's a good point. And so in normal operation, yes. And so if you're pedaling on your bike and you apply force in this direction, if the crank is just going to give just because the whole thing's going to rotate. But when you're doing these static scenarios, so if you think about it this way, we're doing a static simulation of a dynamic situation, right? So normally this bike crank will be rotating. And so in those situations, you have to think about kind of the worst possible case that could happen, that could cause this bike crank to fail. So normally, yes, you apply force in that Y direction would cause it to rotate. But let's say that you're also applying that force at the same time that you're braking. And so that's going to prevent the bike crank from rotating, and that's going to induce that bending. Or maybe your wheel gets caught on something and you're trying to pedal, but that force gets transmitted through there and it's not allowed to rotate. And so you're going to see that a lot in our activities where we have a dynamic situation, but we're limited to a static simulation. And so you have to kind of think about those kinds of worst case scenarios. But it's a good observation because normally it would just keep rotating.
So wait, so why do we select the Y? I mean, yeah, why do we select the Y? Because the thing is that if it's in motion when it's if it's in motion, when you're applying the stress, I mean some of that stress is being transferred to it's just not directly versus like at the end of it stroke. Like if you continue to apply that, like your foot will apply that stress in like a downward direction or whatever, but because it's almost perpendicular to it, that won't really cause it to rotate. It's more like the momentum that just leaves it going. Yeah,
so like I said, we're looking at a worst case scenario where normally it would keep rotating if you apply in the Y direction, right? But if the bike crank were to get caught on something, or you're applying the brake at the same time, you're trying to pedal at the same time, this would be kind of the worst case scenario in that situation.
So it wouldn't work this way,
Yeah, and you can test it too. And so you can run the simulation. You can try putting the force in the X direction. You can observe what the stresses are in that situation, and apply that same force in the Y direction, and you can observe what happens there as well. That's kind of the beauty of the simulation, is that you can you're not just limited to just one scenario. You can test out multiple, and you can see what would be worse. And so a lot of times the results would surprise you in terms of what would be worse. Yeah. Okay. All right, and so in order to run the simulation, we need to specify our output. Oh, actually, sorry, I got sidetracked. So one thing that you should always do, before you hit solve on the simulation, is you should try to make some predictions in terms of, what you should expect in terms of the simulation results. Okay, because remember, going back to last week, right? And so it's when you kind of have a very complex tool like this, it's very easy to always take the results always at face value, but a lot of times, when you run a simulation, when you're setting it up, you're going to make mistakes in terms of, maybe the mesh or maybe the application of the boundary conditions. And so you should always have kind of in the back of your head an expectation in terms of, what you expect the results to look like. Okay. And so I want you guys to kind of get into that mindset in terms of, making that prediction, so that when you do get your results, you can compare the results in terms of what you predict, right? Sometimes they match up pretty well, right? And so if you have a pretty good physical intuition in terms of what to expect, right? Maybe the thing that you don't really know exactly is maybe the exact values of the stress or the exact values of the deformation, but it's going to behave in a way that you predict. Or maybe you run your simulation and it's not going to act the way that you think. And so in those situations, you may have to reassess. And so maybe I applied the boundary conditions incorrectly. Maybe my mesh needs to be improved. Or maybe just the way that I thought about this, maybe my physical intuition was incorrect to begin with, right? But you always need to think about that. And so, I don't want you guys to get into this kind of mechanical kind of mode where you just do the settings and then hit the solve and then just take the result at face value, right? You should always kind of check the results in terms of what you expect. Because that's kind of what separates, a human engineer from, like a robot from doing this, okay? It's the interpretation, it's the analysis of what you're getting. Okay, so next here is we're going to look at our simulation results. And so we need to specify our outputs, okay? So for this simulation, we have 3 outputs that we're going to look at. So we're going to look at the deformation, the normal stress, and the equivalent stress. So let's go ahead and add all of those in, okay? So I'm going to right click on solution A6. We're going to add the total deformation. Okay. We're going to add the stress, the equivalent stress, and then let's also add the normal stress as well. Okay. Okay, good. And so if you continue reading the project specification, there's a little bit of explanation here about what the normal stress exactly represents and how it differs from the equivalent stress. So I'll kind of leave that reading up to you just because, I do want to go over kind of the rest of the activity. Okay. All right, and so we hit solve, and so we can go ahead and run our simulation. Should be pretty quick because this is a pretty simple case. Okay. And so here we have the results. Okay. So if we look at let's look at the deformation first. Okay. And so deformation usually is the easiest to look at. Let me just change my units here so we're in inches. That's a bit more useful. Okay. So deformation is always pretty easy just because we have our fixed support that we know we applied on this side, and we know we applied our force on this side, and so we know that our deformation should be highest as we move further away from the fixed support. So that kind of matches up nicely with that. Okay. We look at our equivalent stress, and so you can see that we've applied this bike crank in bending, right? And so we have a maximum strength, maximum stress above and below the bike crank. Okay. And so what we know from bending is that we know that one of these sections is going to be in tension and the other is going to be in compression. Okay. We don't get that sense from the equivalent stress because remember, equivalent stress just gives us stress magnitude, but we can tell which is in tension and compression by looking at the normal stress. Okay. So if you look at the normal stress, any positive value for normal stress is going to be tension, and any negative value for the normal stress will be compression. Okay. And since we apply the force in the negative y direction, right, it makes sense that this portion here is in compression, and this section up here is going to be in tension. Okay. Just because that's just how bending is, because we're kind of pinching the bottom of the bike crank and we're kind of stretching out the top. Okay, so all that is good. Okay. Okay. All right, and so that is the activity, or at least as far as I'm going to take you. Okay. There are different parts of this activity as well. So the first part that you're going to do on your own is going to be problem 5, which is the maximum load. Okay. Okay. So the type of aluminum that we're using here has a yield strength of 35,000 psi. Okay. So that means that it can withstand an equivalent stress of 35,000 psi and not break. And so anything past 35,000 is going to fail. Okay. Okay. And so assuming a factor of safety of 2.0, what I want you guys to do is I want you guys to alter the magnitude of the force until you reach a stress that's going to be dangerous for this bike crank. Okay. Okay. So with the current loading, so with the 100 pounds of force, the maximum strength that we get is 13,275 psi. Okay. Yours might be slightly different if you're using a different alloy of aluminum. I even forgot what I picked. Okay. So right now we're safe. Okay. So this is well below the yield strength. Okay. So what I want you guys to do first is I want you guys to increase the magnitude of the force until you reach a maximum stress of 35,000 psi divided by the factor of safety, okay? And so in other words, the strength that you should be aiming, or the stress that you should be aiming for is 35,000 divided by 2, which is the factor of safety, which is 17,500. Okay. Okay. So in other words, if you go back to the problem here, and so let's say we increase this force, and so instead of 100 pounds of force, let's do 105. Okay. And so that's going to increase the amount of stress that we experience here. So we go ahead and solve that again. Right, we need to wait for the simulation to finish. Remember, you can look at the bottom left here to check on the simulation progress. Okay. And so you can see here by increasing the amount of force, we've slightly increased the stress as well. So we went from about 13,275 to almost 14,000 psi. Okay, so there is an ideal force here, which gets you right up until 17,500. So I want you guys to find out what that force is. Okay. Now don't go crazy trying to reach 17,500 exactly. So I'm not looking for you guys to hit this number right on the nose. Right. So as long as you're in that ballpark, and so as long as you're in between, maybe 17,000 and 18,000 psi, I'll be happy with that. Okay. So don't go crazy trying to reach 17,500. Okay. But you should be able to find a value of force that kind of gets you within this ballpark. Right. Okay, so that's problem 5, and this kind of showcases kind of a really nice feature of simulations is that you can just go in and you can just modify the conditions and just re-simulate and see what it looks like. Okay, if you were to do this mechanically in the real world, this would take you much longer to do. But with simulations, this just does is just take just the just a click of a few buttons and just the modification of a few settings. Okay. Okay. Problem 6, I want you to repeat problem 5, but instead of having the force in the y direction, I want you to have the force in the x direction, okay? Specifically in the negative x direction, because that's going to put the bike crank in compression, okay? So that's kind of the scenario that you were kind of talking about, where if you were to push on the bike crank, where the bike crank would be either be at the top or the bottom of its motion, okay? Okay, so you're going to repeat the exercise and kind of find that maximum force, and you're going to find that it is quite different, okay? You're going to use the same criteria, so the same yield strength of 35,000 and a factor of safety of 2.0. Okay, so you're going to aim for a maximum stress of 17,500. Okay. Okay. Problem 6 is I want you to summarize your findings. Okay. So this is an important part here because whenever you run a finite element simulation, part of your job is not just to run the simulation, but also to communicate your results. Okay. So that means, most of the time it means writing a technical report, which is what you're going to do on your midterm projects. Your midterm project is to do your own finite element and to write a technical report. Okay. But I don't want you guys to write a full technical report for this activity, just because these activities are more just for your learning. But I do want you to get in the practice of writing, writing ways to kind of communicate your results here. Okay. So think about this as kind of like a brief or like a memo that you're gonna prepare to basically inform your boss of your findings. Okay, and so the report should be no longer than a page, and so don't try to make it too long. And you should try to hit under all of these all this information here. Okay, so you should summarize a little bit about your FEA modeling decisions. And so that includes your choice of material, your choice of meshing settings, the sizing and the order and the shape, your choice of boundary conditions. Okay, so you should communicate, to your boss that, that you've thought about all these things, that your results are going to be reliable. Okay. You should also report on some of your preliminary results. And so, talk about the stress that you are observing under typical loading. You should observe the maximum, you should note on the maximum allowable load under the current design. Okay. And then based on these results, I want you to make a recommendation to your boss about whether the bike crank should either be redesigned or maybe we can save on material and eliminate some parts of the bike crank itself. Okay, and so that's something that you have to kind of determine on your own. Okay, so when you're writing these summaries here, and the same goes for your technical report, you should aim for clarity. Okay, and so try to say things as concisely as you can. Okay, so you don't really get any extra points for being adding too much detail. In fact, it's kind of annoying to read things that could have been said much more clearly. Okay. All right, and so generally speaking, and I'm going to give you guys this advice for your midterm project as well. And so if you're not sure whether your report is clear enough or concise enough, have one of your friends or family members read it. And if they can understand what you're saying, then you're in pretty good shape. Okay. While maybe someone that's outside the class, maybe they can't really understand your FEA modeling decisions, but they should be able to understand kind of the other parts of your report as well. Okay. So definitely do that, and I'll remind you that for these activities, I am mostly grading it on completion. But this is a good time to practice because your midterm project, I'm assigning that tomorrow. And so, I would get the practice in now so that, the report and the midterm project is not going to be as daunting. Okay, and then the final part of this activity is going to be to do another analysis just from scratch. Okay, and so if you go back to the Canvas site, there is a second CAD file that I've posted for a bike frame. Okay, and so I want you guys to do an analysis on that bike frame as well. And so that includes, applying the meshing, the boundary conditions, and looking at the results. Okay. And so I think I've also kind of summarized the boundary conditions that you should apply, and there's some questions that you need to answer here as well. Okay, so that's everything with the activity. So we have 10 more minutes in class today, so feel free to use that to work on the activity. Any questions on anything about the activity 2? Yes.
Are there any considerations we need when saving these type of files?
Yeah, okay, so thank you for I forgot to mention that last time. And so if you want to save your files here, if you're working just on your personal computer, you would just save it from the workbench. And so you would just save it as a project, and you can open it up later. And so if you're working all on the same computer, that's the best way to do it. Okay. The issue with that is that if you're going to be transporting your files from one computer to another, so let's say you're working on the lab computers here, and you're going to be transporting your files home to continue at home, it's a little bit complicated to move those files. Because if you just save it normally here, it's not going to save a single file, it's actually going to save a collection of files that have your geometry, your results, and your settings. And so if you're going to be transporting your results, the best way to do that is to actually archive it. And so to do that, you're going to go back to Workbench. You're going to click on File. You're going to click on Archive. Okay. It's going to ask you to save. So let me go ahead and save it. Just going to give it a name really quickly. Take us to the desktop. That's fine. Okay. And then it's going to ask you to save the archive file. So the archive file is it's essentially a zip folder of your results. And so it's a WBPZ file. So go ahead and save that. Right, Windows is going to open up and ask you what you want to archive. So go ahead and click on Archive. Okay. Okay, and if you go to where you saved it, okay, and let's say that you want to send this project back to your home computer, the one that you should be saving or sending is this WBPZ file. Okay. So don't send this file. So don't send the WBPJ file, because that's not going to open up on your home computer, because then that depends on these other files here. So you want to save the archive file and then move that one back to your personal computer. But if you're just working all on the same computer, then you don't have to worry about that. Just save the project normally. And then to open it up again, you just double click on that. Good question. I always forget to mention that after activity 1. All right, any other questions on activity 2? Okay, all right, and so I will stick around until 5:50. I do have to lock the room at 5:50 though, so if you're in the room today, feel free to keep on working. Remember, the deadline for this activity is coming up pretty fast, just because we're doing another activity on Thursday. So deadline for activity 2 is this Thursday, July 9th, by 11:59 p.m. Okay, so just be aware of that, and so just make sure you're kind of working on that over the next couple of days, so that it doesn't sneak up on you on Thursday night. Okay. But besides that, thank you guys for coming today.
Yeah, I'll be available over email for questions, but yeah, I will see you guys all tomorrow.
So that's okay. So if I do, as long as I save, if it's just gonna be on my computer, as long as I save the project, then and everything else, like across all of them.
Exactly. Yeah. Yeah. So you only have to archive if you're transporting between computers.
Good night.
Yo.
Assigned one, I did do simulation stuff like that. I just want to ask, when you selected, so when technically you gave it a thickness of 5 millimeters, but we did the 2D instead of 3D for the elements. Did you just assign it like a thickness so that way we could actually run a simulation on it, or?
So when you run a 2D simulation,
Yeah.
you're solving a different form of the governing equations. So the thickness technically needs to be there because the overall stiffness of a structure depends on its volume, right? And so a thicker structure is going to have more stiffness, right? And so the 2D equations are going to emulate that, but the structure itself doesn't have any physical thickness because it's a 2D. So the thickness that we assign is essentially, think of it as like another material. And so the overall thickness, it's not exactly this, but you can think of it as like a product of like the Young's modulus and the thickness. That's what we define as stiffness.
These brains, as you asked like a question, what would the basically hallucinate on 5 times? I was like, oh, it would just increase by 5 times.
Yeah. Yeah. No, that's the right observation. The main reason for that is because we're using a linearly elastic material. So
Yeah.
everything is linear. So you increase the load by 5 times, the deformation and the stress.
Which I thought it was a trick question in the beginning, because I was like, I don't know if small people can take that much.
Oh yeah, no, for sure too. And that's the other thing that you get with the linear material is that you don't get that plastic deformation. Because yeah, normally we just either break or you start to have plastic deformation. But if you just assume linear elastic, it's just going to keep going. So yeah, no, that is the right observation to make that.
For this class, like just in general, FEA stuff, it's just for is it for elastic deformation? Is it plastic deformation?
You can do plastic deformation. We're not going to dive too much into it because it does get pretty complex. And then there's other factors of FEA that I would rather kind of go over. But ANSYS does have the capabilities to do that. You just have to kind of build it.
And then when we had that question about the whole or whatever, I was kind of like, because I know from like machine design that basically with there's brittle materials and then there's ductile. In that class, for whatever reason, I think maybe just for the sake of simplicity, we didn't like consider like stress concentrations in ductile materials or something like that. But when I looked it up online, it's like, no, you need to do it. It's just like in fatigue loading, that it could be a little bit different, but that one I was kind of tripped up because I was like, obviously, like if you increase the circle or whatever, then the cross section that you take out the circle will have less of an area, which means the nominal stress is going to be uh, larger.
Yep.
But at the same time, like the actual KT factor, because if you look at the graphs, it always only sits between 2 and 3. So I was like, I don't know how to. I was like, I don't know.
Yeah. So when you're in that scenario, you kind of need to incorporate the nonlinear effects, especially for ductile materials, because those stretch quite a bit.
Yeah.
And so the linearly elastic material is not going to capture that well. So I do have handouts in terms of nonlinear materials and isotropic materials, and so those are all online. So if you want to just check for your own curiosity.
Yeah.
But for the in-class activities and the projects, I am not really going to cover it. Maybe in the last week or so, when we have just a bit more time. But yeah, that is like you said, that is important in certain applications. And ANSYS can do it. It's just just don't have time.
The thing too was about thinking like for a like a hole or whatever. If like I know that what happens is it's kind of like strain hardening near like the edges or whatever.
Yeah.
So when you make a part and stuff like that, like if you somehow like could you just like even if it's gonna plastically deform technically at the edge or whatever, do you still like kind of prevent that like in a sort of design or they just let it like let a part that's ductile material kind of reach that kind of just let it strain harden?
It depends on the application, of course, and so it depends on what that part is designed to do. It's kind of hard to say from activity because that's such a contrived case. Like you wouldn't have just a sheet with a hole for no reason. And so, for a case like this, like you would not want this to strain harden at all. You want it to be stable, all because this is something that people are going to use for a long time. But there are other situations where maybe you would want that. Maybe that's just part of the design process. You just let it strain harden. And then the design's just better in that situation.
Yeah.
I can't think of anything off the top of my head, but I can see that being part of certain design cases.
My another thing is like my machine design, like that's the class when we took it, like that's probably like my favorite class in the whole like degree so far. Like and FEA is like super important. But the thing is like we only did shafts and even these things that you say in class, like I'm just like I don't remember it. Like so I'm just like I'm like struggling to kind of have a conceptual idea of possibly like where the stress would be maximum.
I see.
So like when you said bending, I was like, oh shoot, he's right. Like,
Yeah.
So just like I'm like, I need a review.
Yeah.
Like
I mean part of I think probably a lot of people are in that boat too.
Yeah.
But part of doing a simulation is that you can kind of visualize and kind of really see. And so, a lot of those concepts that you would learn, like solid mechanics, machine design, I think until you see it, I think it doesn't really hit really home. So part of this class is like you run a simulation and then it's more like afterwards you run the simulation, you see the results like, that makes sense from this perspective.
That makes sense.
Yeah. Because the equations don't lie. I mean, the equations are all solved correctly. Now, there are ways that you can mess up the simulation with the mesh and the boundary conditions, but generally, if all those are sound, then the results of what you're seeing should be pretty accurate. I mean, not accounting for things like plastic deformation, nonlinear deformation.
Another thing I do want to ask is like department, because I know that like generally like some of the other schools they have like 2 machine design classes.
Yeah.
I would like if there's somehow is another tech elective that's machine design related, I would take it in an instant.
I see. I don't know. I think probably the closest thing that you would get to that is like a manufacturing class or one of Dr. James's classes. I don't think he's teaching one this fall, but I know he teaches one in the spring. So either it's I think it's literally called advanced manufacturing or something. Okay, that's probably your closest bet. We do have some materials classes as well. I know we have a plastics class. Okay. That's usually taught by part-time faculty. We have a composites class as well. Dr. Sue, I think, usually teaches. Yeah, Dr. Wang teaches. She teaches that one as well. Those are probably your best bets for that. Actually, probably the composites class and the plastics are probably your best bet.
I sometimes I just spend like hours and I'm like, dude, I have to get this assignment done.
Yeah.
like these conceptual ones, because I'm just like, I go in a rabbit hole and I'm
Yeah.
like, shoot, I'm trying to look up all the stuff that I forgot. But yeah, I might just turn it in and just finish it up.
Okay, yeah, sounds
I'm a little
good.
bit behind, but I'm like, well, the assignments are really to prepare you for it. So
Yeah.
they're not worth a lot. So I'm like, okay, I'm a little behind, but I just catch up.
Yeah. I mean, it's good to think about all these things too, because this is kind of where you learn. Like you grapple with material, you kind of, you ask yourself questions, and then you kind of answer them. And it's like, oh, that's where the learning takes place. I mean, it's great that you're doing that. And the assignments themselves aren't worth that much, but yeah, I would still get it in because it's I do accept late work, but there is a penalty each day. So.
Yeah, that makes sense. Yeah, right now I'm working on like with a company. I'm doing like some like I basically do a 3D scan of like a body part or something like that. And then to be honest, like I know a guy and he was able to crack some like really expensive softwares. So I'm trying to learn how to reverse engineer them. But the thing is like I'm trying to figure out how to like apply some design concepts to like from machine design to the like designs that so basically I remake the model that I do a 3D scan of, and then I kind of modify them to look more aggressive or give downforce for a car or something like that. But it's like I need to be able to run an FEA on it.
I see.
And like so like all the stuff you're talking about meshing and this and that, I'm like I've had so many issues like with things being super large and stuff.
Oh yeah.
Yeah.
I mean, if you're, I mean, a lot of people try to teach themselves ANSYS, but yeah, these are all things which, if you don't really know the background, they're just buttons on a screen that you're pushing. You don't really know what you're doing. So yeah, it's good to know all these things because every button, every setting has a purpose.
Yeah, sometimes I ask stuff and I don't think it fully through because I'm just like, I'm here in class and so I just throw it out there. But yeah, I don't know.
Okay, no, it's good. I mean, it shows that you're engaged, and that's the thing that you would want most as the instructor. So
Gotcha.
Yeah.
All right. Well, I'll get this thing done, and then if I have any questions, I'll just
Okay, sounds good.
Thank you.
Yep.